Hello, and thank you for watching my presentation. My name is Mojtaba Ahmadi. I work at the Institute of Material Science and Technology at TU Vienna. The subject of my talk is phase separation in methacrylate-based photopolymers. So let's begin with photopolymerization in additive manufacturing, which is actually a fundamental approach in creating very precise and accurate polymeric objects by using light in various means. That means by combining benefits of additive manufacturing with some of benefits of photopolymerization and the cross-linking reactions associated with them, uh, uh, you're able to make nicely formed polymeric objects that maybe wouldn't be possible to make in any other way. But in order to have such systems on the expected wide scale in industry, certain improvements in the ultimate mechanical properties must be made. What I want to talk about today is really kind of approach that we're taking to improve the toughness of acrylate-based materials that we use in additive manufacturing. This approach is based on using a multi-component system where we can have the desired characteristics of the components in an integrated polymer and therefore having ultimately a stronger and even tougher acrylate-based polymer. Here I brought the general mechanics of toughening consists of having intermolecular interactions, heterogenization, like rubber toughening or in general impurities, strain hardening, which is of course absent in thermoset polymers, and also having reversibly opening of physical bonds. So in comparison to a brittle material, in a tough material we have more of these mechanisms active. Here we can also compare acrylonitrile butadiene styrene or ABS with the polymers made from its building blocks. In ABS, as a tough thermoplast, the essential mechanisms of toughening are implemented. And as you can see in the table, it shows high fracture toughness than polystyrene and styrene acrylonitrile. But on the other hand, we have purely acrylate-based thermoset resins, in which we get kind of inhomogeneous cross-linking uh, that causes the final polymer to be rather brittle. So the objective here is to focus on the heterogenization mechanism, also Z2, to create an ABS-like material from acrylate-based resins that mimics ABS well. In ABS, heterogenization is through a phenomenon called phase separation, where we get butadiene segments into the polymer backbone and also the nitrile groups that are highly polar. And the phase separation is the result of this kind of incompatibilities of these components in terms of polarity. Also, in thermosets, we get some kind of heterogenization by the formation of some domains that are poor in one component and rich in the other one, and by affecting the variables that are involved in the formation of those domains, we can not only adjust the mechanical properties, also we can affect the static properties and shrinkage of acrylates. There are several approaches of inducing and introducing heterogenization to the polymeric systems other than copolymerization and blending, like having fillers in the system or having thermoplastic puripolymers in the system. We can also use the systems in which monomers follow separate mechanisms, like having epoxies and acrylates uh, at the same time in the system. We can also use systems in which all the monomers follow the same polymerization, photoinitiation polymerization reactions. But what we have come across in photopolymerization of acrylates is gelation, at which the phase separation suppresses and shrinkage begins. Afterwards, phase separation occurs, but just locally and is therefore not that effective in determining the ultimate mechanical properties. So the time difference between these two factors, I mean the gel point and the phase separation onset, is very important to be measured and also adjusted by changing the involved variables such as photoinitiator content and um, uh, radiation intensity for affecting the morphology of the final polymer. If there is enough time and phase separation persists long enough, the domains are able to grow so that they are able to refract the visible light, and the final sample will look opaque. So let's go through the materials that we have selected for this work. Uh, uh, the, the components are selected in a way that they can resemble AB as well. So for the oligomer and for butadiene in the ABS, we have selected the functional urethane acrylate in isobornyl acrylate because it has a flexible urethane linkage in the backbone, and since it's highly viscous, it has been diluted. And also for the crosslinker, we have selected the ethoxylated bisphenol A dimethacrylate known as R348C that resembles styrene. They were mixed in the same proportion in the presence of 1% TPO, and they got polymerized in a fairly mild condition in UV light, and the intensity range of 30 to 3 to 30 milliwatt per square centimeter in a matter of 2 minutes. And as you can see, also by increasing the intensity and sufficient amount of photoinitiator, the double bond conversion didn't reach 100%, which means we might still have some unreactive species into the system. Right after exposure, we can see that the material gets opaque, so we get this opaque material, which is a nice indication of phase separation with the domain sizes that can scatter visible light. And by having a look over the chemical structure of the components here, it's obvious that the structure of the crosslinker contains aromatic rings that can give rigidity to the polymer structure and are cause of high glass transition temperature. But the oligomer has, of course, polyurethane segments which are flexible, and such differences in rigidity may have an impact on the reactivity of these monomers and increase phase separation potential. Moreover, uh, the high polarity of the replicated functional groups in SR348C against the non-polarity of Turing compounds in EVOA, and also the planar structure of the aromatic groups in bisphenol A in comparison to the cycloaliphatic non-planar groups of the oligomer would make these monomers more incompatible to each other. When the resulted opacity indicates that the sample is able to get phase separated, uh, it's better to prepare samples for characterization in a thin layer form, because thin samples or films can resemble additive manufacturing process well. And of course, in a homogeneous structure like UV transparent structures, the morphology is independent of depth, so we can select any area for characterization. And of course, in case of thin samples, there is no need to break the sample to have the microstructure. But if we want to break the thick samples, we should do it from X direction in this representation, because it's perpendicular to the direction of light exposure, which is a direction at which the material shrinks. And then the domains might orient unidirectionally perpendicular to the shrinkage direction, which is Y. And of course, the presence of oxygen must be avoided at any stage of polymerization, because it has uh, a negative effect on polymerization. So we get some tacky surfaces which are not easy to characterize on the AFM. Also, in case of highly viscous materials, we need to perform degassing because some bubbles can be trapped into the formulation. And also for characterization, there are methods like atomic force microscopy, scanning electron microscopy, and DMA, among which AFM in tapping mode is very common, which records any change in the cantilever oscillation due to the tip surface interactions. Here, the tapping mode findings are shown, and as you can see, the structure is highly heterogeneous. The domain sizes are in nanometer scale due to the high crosslinker content and high crosslink density. AFM also offers a histogram that statically represents the contrast of mechanical properties, in which low degrees represent hard domains and high degrees represent softer domains. Uh, we can also notice certain linear shapes that are extremely soft and can be assumed to be unreacted monomers resulting from the lower conversion of double bonds. It seems that fractures can also propagate through such lines that are presumably points of weakness. The problem here is that the findings of histogram are relative and contractual, which means we cannot compare the histogram of one sample to that of another one only based on the degrees in this case. Therefore, we employed another AFM mode known as pinpoint mode. And what AFM in this mode does is that it calculates some mechanical properties like adhesion force in this case on the B from a force distance curve and at each pixel. So as you can see, the results are actual numbers in nanonewton for adhesion force in this case, for example. They are comparable and we know exactly to which domain the measured pixel belongs. But you may notice that we cannot see the linear features of tapping mode AFM in this representation, and it seems that a combination of these two mode is necessary to have a clear understanding of phase separation development at the surface of these materials. Here we have the AFM results of the pure sample, I mean just crosslinker. And as you can see in tapping mode on the A, we still have some phase contrast, although the sample is certainly not phase separated. So it does show something, but not something that is necessarily related to phase separation. As a result, I would say that tapping mode results in highly detailed images about the heterogeneities, but its findings need to be confirmed by another mode which is based on actual values like adhesion force or stiffness. Finally, I would say that it's important to consider the chemical structure of the reactants as well as the kinetics of their reactions to induce phase separation in the thermoset polymers made from them. Uh, uh, we need to be also able to affect the time difference between phase separation and gelation to have a nice control over the microstructure and the ultimate mechanical properties. Also, high turbidity is a proper indication of phase separation development, and it's better to prepare samples in a thin layer forms for atomic force microscopy. And a combination of tapping mode and pinpoint mode, which is based on actual values, is advantages in having a nice understanding of phase separation development in thermoset acrylate polymers. At the end, I really wanted to thank the organizers for all the efforts for putting together this meeting, and special thanks to my colleagues at the DigiFot project, especially my supervisor, Professor Jürgen Stampfel, and also to my colleagues at TU Vienna for their wonderful collaborations. Thank you very much.